What if I told you that the empty space between the stars isn't actually empty at all? What if the vacuum, the very fabric of reality itself, was actually a solid, like an incredibly rigid, perfectly ordered, invisible crystal? Now, this isn't science fiction. It's this wild idea at the heart of a brand new paper that could totally rewrite everything we thought we knew about the universe.
Okay, so let's just dive right in. The paper is called Vacuum Elastodynamics, and it kicks off with this absolutely mind-bending line. It's proposing that the space we all move through isn't a void, but it's a real physical substance with mechanical properties, and they call it a Hyperuniform E8 supersolid.
All right, before we go any further, what on earth is a supersolid? I mean, it's a genuinely bizarre state of matter that physicists have been obsessed with for a while. Try to imagine something that has the rigid, ordered structure of a perfect crystal, like a diamond, but at the exact same time, it can flow with absolutely zero friction. It's like a ghost passing straight through a wall. It's both things at once. And this theory is saying that is the fundamental state of our universe.
Now this idea, it immediately throws up a huge red flag for any physicist. I mean, if space is some kind of ordered crystal, like a grid, then wouldn't it have, a preferred direction, a kind of cosmic grain? And if it does, well, we have a massive problem.
This is a great way to think about it. You take a piece of wood, right? It's anisotropic. It has a grain. It's way easier to split it along the grain than against it. A wave traveling through that wood would actually move at different speeds depending on which way it's going. But we know, for a fact, that the vacuum of space is perfectly isotropic. The speed of light is the same no matter what direction you're traveling. This is one of the most precisely tested facts in all of science.
And look, this isn't some small technical detail. Having a directional grain in the vacuum is a complete and total deal-breaker. It would violate one of the absolute pillars of modern physics, Einstein's principle of Lorentz invariance, the core idea that the laws of physics are the same for everyone, everywhere.
And it's not like they're the first people to think of this. The paper points out that there have been other world crystal theories. Pioneers like Kleinert explored this, but they all got stuck on this exact same problem. It was like a brick wall they just couldn't get through.
So, the crucial question is, how does this new framework, this vacuum elastodynamics, succeed where all the others have failed? How does it possibly square the idea of a crystal vacuum with a perfectly constant speed of light?
The answer, according to this paper, is an incredibly elegant and kinda hidden property of this specific crystal structure they chose, which is a mathematical object called the E8 lattice. The key is something they call exact sublattice symmetry. Let's see how this works. The best way to picture this is not as one single grid. Instead, what the paper shows is that the E8 lattice can actually be broken down into two identical, perfectly interpenetrating sublattices. So imagine two identical crystal grids just perfectly woven into each other at every single point in space.
Now, this perfect symmetry, it isn't just some neat geometric trick. It actually creates a really powerful mathematical law, something called a topological Ward identity. You can think of this thing as like a cosmic referee, and its one and only job is to absolutely forbid any directional difference from ever showing up. It's a fundamental rule that keeps everything looking perfectly smooth.
So how does this cancellation actually work? Well, the first sublattice, all by itself, would create a grain. It would totally mess with the speed of light. But then, the second interwoven sublattice creates an equal and perfectly opposite grain. The two effects are so perfectly balanced that thanks to that cosmic referee, they cancel each other out completely, at every single point and in every single direction. So the net result? The vacuum appears perfectly smooth. And here's the brilliant part. The grain, that anisotropy that should be there, it isn't actually gone. It's just perfectly hidden by its identical opposite twin. This theory somehow manages to keep its crystal structure while also preserving Einstein's most cherished principle. The paradox that stumped everybody else is just elegantly solved.
Okay, so we have a rigid crystal lattice for a vacuum that, miraculously, doesn't affect the speed of light. That's one huge puzzle solved. But it immediately opens up an even deeper question. If the vacuum is a rigid grid, how does matter itself even get mass? How can anything move through this solid universe at all? We'll dive into that in our next explainer.